Good day everyone, good day. In this presentation we are going to answer physics question on radioactivity. Okay, so here the question reads, a radioactive isotope X has a half-life of 600 years. What fraction of the radioactive isotope X decays after 12,000 years? Okay, so here we need to find the what would decay after 12,000 years. Then B, the activity of a freshly prepared radioactive isotope X is 4,000 counts per minute. How long will it take the activity of the same to 4 to 500 counts per minute? So here we want to calculate time. So first and foremost we need to understand when we talk of half-life. Okay, so half-life, this is the half time taken for a radioactive atom to decay or radioactive substance to decay. Okay, so now here we are going to answer the first one, which is A, to determine the fraction that has decayed after 12 years. So now this one, what have we been given here? So the formula that we are going to use is this one, where we talk of this is A, we talk of nt. This one represents the time, the amount of radioactive that remains. Then this one N or E represents the initial amount, okay, or initial amount of a radioactive substance. Then here we have half, then to the power n, where this n represents the number of half-lives. Okay, so now in order for us to find this n, we say n is equal to total time taken over half-life. Okay, so here we have, this is half-life. So now, having this information, we have been given the half-life, which is 6,000 years, and the total time that it would take for this radioactive to decay, it's what, 12,000. Okay, so now here we are going to use this formula to find the number of half-lives. So say n is equal to, where there is t total time, we are going to write 12,000, then over 6,000. Okay, so here we can cancel these zeros, this 0, then 6 into 12. Here we say n is equal to 2 half-lives. Okay, so this is n represents 2 half-lives. Then here now what we want to calculate is what's the fraction. So in order for us to calculate the fraction, we're going to divide by this initial, this side. Okay, so even this side by n. What you want is the fraction. So whenever you are told just to calculate the fraction, you just need to consider this formula. Okay, if at all you can't use the other formula, you can use this side, where this one represents the fraction of a substance that will remain. So here now, where there is n, you replace we will replace n with what? 2. So we'll say where there is n here, we have half like this, and then there we'll say 2. So now here, which means that each number here is raised to power 2, even this to power 2. Then what are we going to have? So here we are going to have a 1 squared is just 1 over, then 2 squared is just what? It's just 4. Okay, so now this is the fraction that that remains after 12,000. So here 1/4, it is the fraction that remains after 12,000. So here we are saying that this is the fraction that remains after 12,000. Okay, then the question here is asking us to calculate the what fraction of the radioactive isotope X that decays, okay, after 12,000. So this, if I thought the question was to give the answer of the fraction that remains after 12,000, this would have been an answer. So now here the fraction that remains after 12,000, we know that the total fraction of all these counts, it is equal to what? To 1. So we will just subtract 1/4 from what? 1. So here we'll say the total here, it's what? It's 1. So here we'll say 1, take away 1/4. Okay, so 1 take away 1/4. Well, you can use a calculator, or you can just say there is over 1. So say 1 into 1, it will give us what? 1 into 4. Common denominator here is 4. So we are simply subtracting this 1 from what? 4. So once you do that, or you write this on your calculator, your answer is going to be 3/4. So 3/4 is the fraction that decays after 12,000. Okay, so this is the decayed fraction. Decayed fraction after 12,000 years. Okay, so here if I told this was that remains, then that what would decay is what? 3/4. So here first thing, we've just calculated what remains after 12,000 years, and then we subtract from what? The total amount, or the total number of what? That can what? Decay. So the total amount that can decay, it's what? It's 1. Okay, so you can term this as a fraction, or just like this. Once it is 1, which means it's 100%. Okay, so since it's a fraction, it will be 3/4. Okay, so this is the final answer, and you get your full mark. Then the second one, the activity of a freshly prepared isotope X is 4,000 counts per minute. How long will it take the activity of the same to 4 to 500 counts? So here we have these two here. We have this one here, 4,000. It is the initial. So remember, I gave out this formula to say this one, any t here, it represents the amount that remains. Okay, the remaining amount. And then any or it represents the initial, where n represents the number of half-lives. So here what they want is how long they want the total time here, which is this one. It's the one that they want, and this is the half-life. So the half-life, we know it is what? 6,000. Here we have already been given the half-life to what? 6,000 in the information. So we use this formula again to calculate the value of n. Then from there we are going to use this formula to calculate the value of what? The total time that will remain, or that will take for this radioactive to fall to 500 counts per minute. Okay, so having that, we are saying that here B is N T, which means the remaining, then N O half, then which is the initial. Here it's half to the power n, half to the power n. So having this, we know that any t here, the remaining one here, that is falling, we have been given is 500 counts. So here we'll say it's 500 counts. Then again, the initial here, it's 4,000. So n or it is what? 4,000 counts. And the half-life, it is like this. Half-life here, it's 600, or sorry, 6,000. Then n here we don't have. Then how long the total time taken, again we do not have. Okay, and what they want is this one. So we use this formula to calculate the value of what? N, number of what? Half-lives. Okay, so here we are saying that where there is this one, we replace, or we can also do the same, whereby we divide throughout by n, like this, even this side by n. Then this and this will do what? Will reduce. So here we are going to remain with nt over no is equal to, so sometimes they can also use you can also use m, the letters of your choice. So even m is being used, or n, okay, to represent the number of these substances. So here where there is t, we replace by 500. So here we say 500. Now where there is n, this one represent by 4,000. Okay, 4,000 replacing by 4,000 is equal to, here we don't have the number of n, so here we can reduce this one and also this one. There will remain with 5, and here will remain with what? 40. Then how many times can 5 go into 40? So 5 there, it's 1. Okay, so 5 there, I'll say it's 1 over 5 into 40 is what? 8 is equal to, here we have 1 over 2. So we have something like this. So even this this value here, we can write this in an index notation so that it can equal to this one. Okay, so the number that you can multiply with it to give you what? 8. It's what? 2. So you can multiply 2 3 times. Let's say 2 by 2 by 2, get what? 8. So it's 8 raised to power 3. So here we'll say it's 1 over 2 to the power 3 is equal to, open bracket, half, then to the power n, like this. So here we are saying that 2 times 2 times 2 it will give us what? 8. This is the reason why we've written this one to the power 3. So here this one can reduce and this one will do what? Will reduce. What will remain with is just n is equal to what? To 3. So here our n is equal to 3 half-lives. Okay, so having this 3 is not our final answer. What we are calculating here, it's how long will it take. So we are calculating time. Okay, so now here to calculate time, then we are going to use the formula. So let me do like this. We are going to use the formula of half-life, where we said n is equal to total time, the one that we are calculating, over half-life. Okay, so here for n we can say our n now is equal to what? To 3. So here we are calculating this one in simple terms. We are saying that we are doing t is equal to n times n times half-life. So here our n is 3, t is equal to n is 3 times half-life. Here is 6,000, so replace by 6,000 here. Okay, then t by 3 times 6. Here what are we going to have? Here we are going to have 18,000 minutes. Time, remember, is given in minutes, so here we'll say minutes. So if at all we had days, we would have said what? Days, or years, we would have said what? Years. So this one is given in sorry, not minutes. It's time, we have been given in years, so here we'll say it's 18 what? Years. Okay, not minutes, because half-life is being given in years, but the count rate here is being given in minutes, as you can see. That's why I've said 18,000 minutes. So here we can change this one to years. Okay, so we can just say years. So I'll just cancel this and say 18,000 years. So this is the total time that will take for a radioactive substance to decay or to remain to 4 to 500. Okay, to 4 to 500, which is this one. So it will take 18,000